Welcome to the Explainer. Look, if you're a focused learner gearing up for a massive exam like NEET, and you've got your eyes dead set on one of those coveted government medical college seats, you are in exactly the right place today. We're taking a seriously intensive organic chemistry coaching lecture and condensing the whole shebang down into a punchy, highly structured synthesis. We're cutting all the fluff, we're giving you exactly what you need to succeed. Let's get right into it.
Here's our roadmap for today. We're going to start with a new strategy for NEET, then breeze through electrophiles and nucleophiles, types of bond cleavage, the free radical mechanism, the game of hyperconjugation, and finally, identifying halogen compounds. This is going to guide us smoothly from exam mindset straight into the heavy-hitting chemistry concepts without overloading your brain.
All right, Section 1, New Strategy for NEET. There is an absolute golden rule for this exam. You need to improve the silly mistakes from last time and convert them into a government medical college seat. This is your golden opportunity. Whether you are hovering right on the borderline last time or your new target is suddenly Ames, the secret isn't necessarily learning a million brand new things from scratch. Honestly, it's about rigorously, ruthlessly eliminating those frustrating, silly mistakes. So how do we actually pull that off? Well, the do's are pretty straightforward. Show up to your live classes and be strictly on time. Every single minute counts. The don'ts are just as important. Stop worrying about rumors or when the exact exam date is going to drop. Let's be real, whether you have 15 days or 2 months, your job is exactly the same. But here is the absolutely crucial point. You've got to focus on interconnected concepts. Don't study tests, mechanisms, and rules in isolation. Connect them. If you group interconnected concepts instead of just memorizing randomly, you can literally master all of hydrocarbons in just 40 minutes. It's a total game changer. Okay, let's dive into this next part. Section 2, Electrophiles and Nucleophiles. Let's start with the basics. An electrophile is an electron-deficient species. The name literally translates to electron-loving. Because they are deficient in electrons, they naturally act as an acceptor for an electron pair. And logically, since they're missing electrons, we generally expect them to be carrying a positive charge. But wait, is every single positive charge an electrophile? This right here, this is exactly the kind of assumption that leads to those silly mistakes we were just talking about. Let's see why the answer is a resounding no way. Check this out. Ions like sodium, potassium, ammonium, and hydronium, yeah, they all have positive charges, but they have completely full octets. That means they are absolutely not electrophiles. To be a true electrophile, a species must have an incomplete octet, like a free radical, or it has to have vacant d orbitals. Think of this brilliant analogy from our source material. You can't invite guests to your birthday party if you don't have a vacant room in your house for them. No vacant orbitals means no electrons accepted. Oh, and notice that last point, compounds with polar pi bonds, like carbon dioxide, sulfur dioxide, and sulfur trioxide. They can also act as electrophiles, even without a positive charge. Moving right along. Section 3, Types of bond cleavage. When breaking bonds, there are 2 main paths you can take. In homolytic cleavage, the atoms basically share the electrons equally because there's zero or practically zero electronegativity difference between them. This puts the bond perfectly evenly, creating uncharged free radicals. It's triggered by high temperatures, UV light, and nonpolar mediums. Now, on the flip side, heterolytic cleavage happens when there is a high electronegativity difference. One atom just hogs the electrons, creating positive and negative ions. And notice the logic here. Because heterolytic cleavage forms charged ions, it naturally needs a polar medium, like a polar solvent, to stabilize them. Homolytic cleavage, forming neutral radicals, is totally fine in nonpolar solvents. Now, what's really interesting about this next concept is how we apply that homolytic cleavage. Section 4, Free radical mechanism. All right, let's break down the 3 distinct steps of the free radical mechanism. Step 1 is chain initiation. This is where heat or light breaks a bond homolytically to kickstart the radical formation. Skipping to step 3, chain termination, that's where 2 radicals crash into each other, pair up their single electrons, and bring the whole reaction to a halt. But step 2, chain propagation, that is the star of the show. This is your rate-determining step, or RDS. During propagation, a radical abstracts a hydrogen atom from the alkane. Because this step is the absolute slowest, it completely dictates the overall speed of the reaction and determines if your final product is actually going to form at all. To really grasp the reactivity of different halogens in this mechanism, imagine a morning timeline. Let's say at 9 a.m., you try to react your alkane with fluorine. Well, it is highly explosive. Fluorine is so aggressive it reacts instantly, literally even in pitch darkness. By 10 a.m., you bring in chlorine.
It's a bit calmer, it needs some temperature or sunlight to get going. At 11 a.m., bromine steps up to the plate, needing an even higher temperature to react. And finally, by 12 p.m., we get to iodine, which, as you're about to see, practically fails to push the reaction forward at all. So why does iodine fail? Well, let's call this iodine's smile. Iodine's bond is actually the easiest to break because the atom is just so massive, but it smiles at you and tricks you because the reaction is highly reversible. As soon as this iodine radicals form, instead of attacking the alkane to give you that sweet substitution, they just look at each other, pair right back up into a stable I2 molecule, and essentially go on a little tour, completely useful for your desired substitution reaction. Which brings us to structural stability. Section 5, the game of hyperconjugation. You know, the secret to stability lies entirely in the alpha carbon. An alpha carbon is the carbon directly adjacent to your active site, whether that's a free radical, a carbocation, or a double bond. And crucially, it has to have alpha hydrogens attached to it to provide that stability through hyperconjugation. The trick here is beautifully simple, honestly. Just draw a physical circle around your active site on the page, look at the immediate neighbor carbons, and count their hydrogens. The more alpha hydrogens you have, the more stable the compound is. It practically solves the entire mystery of major versus minor products for you. And this brilliantly illustrates the real-world impact of these molecular structures. Let's compare two isomers, cis-2-butene and trans-2-butene. Because the cis form has its bulky groups crowded on the same side, its dipole moment is higher, which drives up its boiling point and its solubility. But that same crowding causes repulsion, meaning its overall stability is actually lower than the trans form. The trans form, with its groups on opposite sides, packs together much better, giving it a higher melting point and greater stability. But hey, remember our alpha hydrogen counting trick? If you put isobutylene next to these two, it beats them both in stability hands down, simply because its branch structure gives it 6 easily accessible alpha hydrogens. Almost at the finish line, Section 6, identifying halogen compounds. All of this mechanism knowledge is useless if we can't identify the structures. There are some common naming conventions that constantly trip students up. When you see N-, like N-butane, it simply means normal, a straight linear chain with absolutely no branches. Iso means you have a branch, specifically 2 methyl groups sitting on the carbon right next to the end of the chain. Secondary, or sec, tells you exactly where the action is. Your radical or halogen is sitting right on a 2-degree carbon. And finally, neo. Please burn this into your memory right now. The neo prefix strictly requires a minimum of 5 carbons to even exist. Take neopentane, for example, which famously yields only one single type of radical. So the crucial point for classifying these compounds is this. You shouldn't just memorize molecular shapes. Always check the hybridization of the carbon attached to your halogen first. If the halogen is on an sp3 hybridized carbon, meaning a carbon with only single bonds, and that carbon is next to a double bond, it's allylic. If that sp3 carbon is next to a benzene ring, it's benzylic. Now, on the flip side, if the halogen is stuck directly onto an sp2 hybridized carbon, meaning directly on the double bond itself, it's vinylic. And if it's plugged directly into the sp2 carbon of a benzene ring, it's arylic. Check the hybridization first, and I promise you will never get these confused. Which brings us to our final, ultimate question for you. Have you eliminated your silly mistakes, and are you finally ready to ace your chemistry test? By stopping the rote memorization, grouping those interconnected concepts, and focusing on the underlying mechanisms like we did today, you are completely changing the game. Take this highly structured, focused approach right back to your study desk, master these concepts, and go claim that seat. Thanks for learning with us, and we'll see you next time on The Explainer.